Swayam Prabha. Digital India. Educated India.
An IIT person promises only what he can deliver, and an IIT person delivers what he promises.
Friends, welcome you all to this new topic. It's a pipe flow. In fact, till now we were discussing most of our topic that were related to open channel flow. But today we will be starting our new topic, that is pipe flow. As we know that water in the nature we find that these are flowing through open channel, that is rivers, streams and all. But when we come to man-made things, suppose we are trying to carry water from one point to other, or maybe any other fluid when we try to carry from one point to another point, like say it may be oil, it may be water, it may be any kind of fluid, then many a time we take help of the pipe, that is we carry those things through pipe. Well, of course, when for carrying water into the agricultural field, we use canal. That part we have already discussed. But when we try to carry water through some closed conduit, that is, suppose we do not want interaction of that water with anything outside, then mainly we prefer this sort of pipe flow. And there are some other advantages, of course, by carrying water through pipe flow. And that's why when we do this design that okay, we are trying to carry water from say one point to another point, that is from the source. One point means where our source is available, and from that source we are trying to carry the water to some other point. When we talk about water distribution system, say in a city, then say our water may be available from a source where maybe we are doing treatment, we are treating water, and then we are collecting the water, and from that source we need to carry the water to far distance. Then there are some important points. Say we are using pipe to carry the water, that we call it the delivery pipe. Well, now water from one point to another point will be carried when there is a energy difference. As we know that when there is a energy difference, or when there is energy at the upstream is higher than the energy at downstream, then only the water can flow. So in pipe, when the water is flowing, during that process of flow, like open channel, there will be also some resistance offered by the pipe, and that way some energy will get lost. And in that process, the available energy will gradually reduce. And if we do not design the pipe in a proper way, then our intended purpose, suppose we thought that water will be carrying up to a certain point, the water may not be receiving that point because water will not reach that point because say required energy may not be available. Similarly, some other problem may arise, like say when as we know that water in the pipe flows in full flow, it always flow full, means there say in open channel flow, the fluid flow as under atmospheric pressure. So it is flowing with a free surface in open channel, but in pipe it is flowing full, so it is under pressure. Now in our design purpose, this is another necessary point, that what is the pressure that is being created inside the pipe. If that pressure is very high, and if that pipe material is not of sufficient strength, then it may happen that the pipe may burst. So for all those design activities, we need to know the hydraulics of pipe flow, and that's why we'll be starting this topic, that pipe flow, what are the losses there, and how we need to design this sort of pipe flow to carry our water from sources to our required destination. Well, then just to recall what we did, or what are the relevant topic that we have discussed earlier. Well, say if we just recall our very first class of open channel flow, there itself we did discuss what are the differences of pipe flow and open channel flow. In fact, there we did discuss a lot of things about pipe flow also, although our basic objective was to discuss open channel flow. And at least just now, as I have mentioned that point, that major difference between open channel flow and pipe flow is that in open channel flow the water flow under atmospheric pressure, and in the pipe flow the water flow under pressure. That is one of the major difference that we could see. So if you refer to this slide, I am just pointing out that in pipe liquid flows under pressure. This is one of the important point. And then so far this hydraulic gradient line is concerned, say in open channel flow we did draw our hydraulic gradient line. In fact, hydraulic gradient line in open channel flow is nothing but the surface of the water. But here we do not have a surface of water because the pipe is flowing full. So we are not having a free surface. So what will be our hydraulic gradient line? That we need to know. Just we are repeating what we did discuss in our very first class of open channel flow. Well, if the pipe is there like that, then say water is flowing, then if we consider a datum, well, if I take two sections, say this 1 and 2, and from the datum, this is say our datum, and from the datum, generally in open channel flow we did measure it up to the bed, but here we are not talking about any bed because it is not like that. We do not have a free surface, neither we have a bed. So we talk about the center line. So this is center line of the pipe, and then depth from the datum up to the center line is the elevation head, say J1, and then the pressure, there will be some pressure. Now if we insert a piezometer here, then because there is pressure, water will start rising in the piezometer, and it will go up to that height where say pressure at this point will be just balanced by this height. It will be just balanced by this height. So this height we call as P, that is pressure by W, P by W. Okay. So this is the difference between open channel flow and the pipe flow, and above that you will be having the velocity head. If the flow here is having velocity v, then the energy due to velocity is same v square by twice z that we can have. Well, if the section is 1, we are marking here 1 and 2. So for the 1 we can put P1 by W. Then in the section 2 this will be Z2. Then say we have up to this much the water is rising in the piezometer, and then that height we refer as say P2 by W, and then above that we have V square by twice Z. This is the energy head. As we did discuss about this point earlier also, I am not discussing in more detail, but of course just to recall what we did, we are just placing this point. And then the line joining this point to that point, that is, which is say equivalent to the surface of water. That means if we do not keep any barrier, water will be rising up to this point because there is a pressure. So that point we are considering, and here we are considering this point, and that way the line joining this point and that point, that is we call as say hydraulic gradient line. Okay. So this will be hydraulic gradient line. And the head, if we join this total head, means energy total energy, then velocity head is also coming. Then if we join these 2 points, then this is the energy gradient line. Energy gradient line. Okay. Well, now the head from the datum up to this point, that is Z1 plus P1 by W, or in general we can say Z plus P by W. This Z plus P by W total is called piezometric head. Okay. So, what is piezometric head? Piezometric head is equal to Z plus P by W. In some book you will be finding the symbol gamma to represent unit weight of water, and of course it is W and gamma is used, both is used to represent unit weight of water, and here we are writing W, and that way Z plus P by W is the piezometric head. And that is also important in the analysis of pipe flow, because in many a time we see that what the energy here is, because the velocity, because why we are emphasizing on this particular point, because generally pipe will be a man-made structure, and in a man-made structure we generally made the pipe of, say, diameter of the pipe at this point, say section 1 and section 2 will not be different generally, if it is not a converging pipe or diverging pipe constructed or made with a particular intention. Otherwise, for normal pipe, as you see, the diameter between 2 points will be same, that is it flows with a uniform diameter. Now, when it is flowing with a uniform diameter, the point is that discharge flowing through the pipe is constant. Now, if discharge flowing through the pipe is constant, then what about the velocity? When the diameter is uniform at every section, then the velocity will also be equal. I mean, area will be equal, so discharge by area, that will also be equal. Now, therefore, the velocity between the upstream point and downstream point may not have that much difference. Well, now if it is not having that much difference, main energy difference is coming because of Z plus P by W, and that is why this piezometric head, what is available at upstream and downstream, is more important here. Well, with this introduction about some of the fundamentals, which of course we did discuss in our class earlier, we can now go to the actual topic of pipe flow, and let us see that in pipe flow, as we are discussing, that energy loss is important. I mean, knowing about the energy loss is important, and pipe flow, the governing force are there. Say in open channel flow, we were using a dimensionless number in most of the analysis. Say for hydraulic jam and for other sort of analysis, we are talking about Froude number, because in that flow problem, in say open channel flow problem, the gravity force is more dominating. Well, but in pipe flow, the viscous force is more dominating, and that is why we talk about Reynolds number here. In most of the analysis, we will be using the Reynolds number, that will be playing a very important role, a Reynolds number. So, that is why it is important. And how it came, basically, first Reynolds, the scientist Reynolds, Osborne Reynolds, in 1883, he first demonstrated that there exist two types of flow in pipe. He first observed the existence of two types of flow in pipe, and that he did through a simple experiment known as Reynolds experiment. Okay. Well, when he was conducting this experiment, this Reynolds experiment, it is like that he was using some dye, some color, pigment, and then that dye was put, so water was flowing through a pipe, and then he allowed the water to flow through a pipe, and he had the device that he can increase the velocity, he can decrease the velocity in the pipe by controlling some valve, and then he applied some dye, and that dye shows the path of the fluid particle. Well, so when the flow is occurring through a pipe, if a dye is just added in a small quantity at a particular point, if the flow are flowing in a laminar way, that means in a lines, the streamlines that are flowing through the pipes are parallel, then the dye will also be seen as a straight line. Well, and then we can understand that this is a type of flow where the particle of the fluid are moving in a very streamlined pattern. Well, then if we gradually increase the fluid velocity, a time will come when the fluid particle will be starting mixing up, and then it will gradually increase, and then at one point all the fluid particle will be mixing up, and although we are putting the dye at a particular point at the entry, but just when it starts flowing it will get mixed up and we will not find a trace of the dye. So that indicates that, well, up to certain velocity the flow, after certain velocity the flow is behaving in a different way. Of course, although I am saying that it is a certain velocity, but well, in the experiment we can find that velocity we are increasing and then it is happening, but velocity is not the only point, which influence this sort of change in flow pattern, because say with that velocity, suppose in a particular velocity, in a particular diameter, we are finding that okay, the fluid is getting mixing up, but the same velocity if we allow to move with a very small diameter pipe, then we may find that okay, that sort of mixing up is not happening. That means it depends on the diameter of the pipe also. Again, suppose the same velocity is flowing, water is flowing with the same velocity, and at that velocity we are finding that it is getting mixed up, water is getting mixed up, but in place of water, if we replace this water by oil of high viscosity, then we may find that yes, the flow is not getting mixed up. So it indirectly means that if we just say the index as velocity, if we just define that if the velocity exceeds this particular value, then it is a different type of flow where it is getting mixed up, which of course we can name now, because we have already discussed in open channel flow also that there are two types of flow: laminar, where the flow particle moves in lamina, or say fluid moves in lamina. Here we can say the streamlines are moving parallel to each other. That type of flow we call as a laminar flow, and when these streamlines get mixed up, and then we call that flow as turbulent flow. Well, now if we just define that beyond this velocity flow become turbulent, this will not be sufficient. So Reynolds did this experiment, and he did use a non-dimensional number Re, which we know that what Re is. Re means that is the Reynolds number. Well, he did use this non-dimensional number as index to show that up to certain limit of Re. Well, if you just forgot the expression for Re, we can write it is rho V, okay, let me write L by mu. Rho V L by mu is the Reynolds number, but this L is not the length of the pipe. This L basically in Reynolds number, we use this L as characteristic length. Now what is meant by characteristic length? Say in case of open channel flow, we can use to represent this characteristic length hydraulic depth or hydraulic radius sometime. And in pipe, to represent this characteristic length, diameter of the pipe is considered. Well, so this is written basically in pipe flow always as rho V D by mu. So D is the diameter of the pipe, V is the velocity of the pipe, rho is density of the fluid that is flowing through it, and mu is the viscosity. Mu is the viscosity of the fluid. Well, so all these, if we just combine, this forms a non-dimensional number, and that was used as index to indicate whether the flow is laminar or the flow is turbulent. Well, so, and what he could observe that up to certain limit of Re, the flow remain laminar, and beyond a certain limit of Re, the flow becomes turbulent. And what is the range? That range of Reynolds number, he could observe that when this Reynolds number is less than 2000, up to 2000, that means Reynolds number up to 2000, the flow is laminar. Okay. This is different from what we did discuss in open channel flow. In open channel flow, we could find that when Reynolds number is less than 500, then the flow remain laminar. But in pipe flow, when Reynolds number even up to 2000, the flow will remain laminar. Well, and then when Reynolds number is, this is the limit or limiting value in the lower side, below this point it is laminar, and then if it exceeds this value, then flow will not be laminar, flow will no more remain laminar. We are not saying that when the Reynolds number of the flow exceed 2000, then the flow will become turbulent. We are not saying that. What we are saying, that when the Reynolds number exceed 2000, flow will no more become or no more remain laminar. Well, then there is a upper limit again. When Reynolds number is greater than 4000, then the flow become turbulent. Well, though these limits are given 4000, 2000, but experimentally when we observe, we can have some difference. Again, some author gives that these ranges are a little bit different, but anyway, we can just follow that this is the order of Reynolds number at which the flow up to which the flow remain laminar, and beyond which the flow becomes turbulent. Well, that means between 2000 and 4000, what we will call that? Well, this is lower limit and this is upper limit. Upper limit in a sense that beyond this it is turbulent, lower limit in a sense then below this it is laminar, and in between, when the Reynolds number between 2000 and 4000, this range we call as transition flow. Okay. So, Reynolds number, if it is say less than 4000 and it is greater than 2000, that range we call transition. Okay. Now, these Reynolds number, why we are discussing here the ranges, the laminar and turbulent, what is the significance of that? Because based on these Reynolds number, we will able to say whether the flow is laminar or it is turbulent. Now, what benefit we will be getting by saying so? The very basic intention is that if the flow is laminar, then the resistance offered by the flow or offered in the entire system to the flow will be different from that when it is turbulent. That means, what we can say significance of type of flow, that is the resistance offered to the flow. In fact, the energy loss, when we are saying that resistance offered is changing, then energy loss is also changing. So, energy loss is our main important issue. Now, energy loss will be different if the flow is laminar, energy loss will be different if the flow is turbulent. And so, for calculating those things, for engineering those issues, we will be having different equation for laminar flow for calculating loss, and we will be having different equation for turbulent flow. Well, let us see how these things varies. Well, frictional resistance, first let us talk that flow from one point to another depends on the difference of energy level between these points that we have already explained. And then the pipe boundary, now resistance, okay, energy level between this point, and what is energy level that we have already explained. The pipe boundary and the fluid viscosity, as I am saying that viscosity is important here. So the resistance offered is not only coming from the pipe boundary. In fact, in some cases the boundary friction is not that much important. Rather, the friction or resistance offered due to viscosity, that is the resistance offered due to shear stress between different layers within the flow, is more important or more dominating sometimes. So that way what we can say, the pipe boundary and the fluid viscosity offer resistance to the flow. Well, then when there is resistance, to overcome this resistance, fluid need to do some work. Well, so when the fluid is doing some work, that means some available energy, some of the available energy get consumed. Well, and therefore if suppose total energy get consumed, whatever energy was available, if all the energy get consumed, then the water will not move, because everything need energy to move. So there will not be, suppose energy at upstream and downstream become equal, then there will be no flow. Like current, say if there is no voltage difference, there will not be any current flow. Like that, in case of water, if there is no difference in plasmatic heat or say total energy heat, then there will not be any flow. And that's why this is important. Therefore, estimating head loss in the pipe is of great importance, and that's why we will be discussing first in this topic of pipe flow how we can estimate the loss due to this friction or due to this viscosity. I mean, in different type, how we can estimate the losses. That is very, very important. And resistance offered to the flow depends on the type of flow, as we have already explained. And so now we will be discussing in very distinctly that what are the laws that shows that in laminar flow what are the laws of friction loss, then in turbulent flow what are the laws that we have for say friction loss. So first we will be discussing laws of fluid friction. What are the laws that we need to see? The laws of fluid friction for laminar flow. Well, laws means how these laws are being drawn. Actually, based on observation and experimentation. So people are conducting experimentation and they are observing how the friction loss or the loss in a pipe are behaving, and from that these can be find out. And of course, this can be analytically we will be deriving, and then also we will be finding that yes, the equation that we are getting, that also says the same thing. But first we need to understand the things physically. Well, that the loss, or say rather saying first loss, we can say that fluid friction, it is proportional to the velocity of flow, that is in laminar flow. If the flow is flowing as a laminar flow, then the fluid friction that will be offered, that is proportional to the velocity of flow. Okay, and it is independent of the pressure. As we know that fluid will be always under pressure when it is moving as a pipe flow, but the amount of pressure, under what pressure the fluid is moving, that will never indicate anything about the frictional loss or say fluid friction. So that is independent of that. That means if a fluid is having under high pressure or one is under low pressure, whatever it may be, that high pressure flow, whatever loss will be there if the flow is laminar, or in a low pressure flow, whatever loss will be there if the flow is laminar, other things remaining same, that will be same. It is independent of the pressure. Then it is proportional to the contact surface area. This is of course obvious, because friction is coming from the surface as well as of course from the viscosity. But if the contact surface area of the pipe is increasing, that means if the pipe is longer, then the friction loss will also be more. So it is proportional to the contact surface area. Then of course it is independent of nature of the surface. That is interesting. That is interesting. That it is proportional to the contact surface area. If the contact surface area is more, well, the friction loss will be more, or friction will be more, we can say. But in laminar flow, the nature of the surface, that is how rough it is, how much rough the surface is, that becomes sometimes irrelevant. And the reason is that, in fact, in laminar flow, a layer forms on the boundary of the pipe which is in rest, and that always it is like that the water in laminar flow is flowing layer by layer, and that which is static layer, which is not flowing at all and which is in touch with the surface, this make a situation as if the water is flowing over that layer, and that's why the frictional characteristic is not making that much difference. Of course, if there is a large projection, then the situation will be different. In fact, that will create the flow turbulence at that point. That is a different issue. But if laminar flow is flowing, then the surface characteristic sometimes do not influence. Sometimes means in general do not influence, but of course, as I am saying that if projection is very large, then it will influence the rather it will make the flow turbulence at that point. Well, then affected by, that means this fluid friction is affected by variation of temperature. If it is laminar flow, then the fluid temperature is important. That is, if we change the temperature of the fluid friction changes. That is why in experimental study, when we conduct experiment on this friction, then we say we always do with different temperature of the fluid. There, in fact, in those experimental setup, there is a device by which we can change the temperature, and that way we can see that if we change the temperature, then how the fluid is behaving or how the resistance is generating there. So, it is affected by the variation of temperature. Why? Because with the change of temperature, basically the viscosity, as we know that from our very fundamental knowledge of fluid mechanics, that viscosity is a property which is influenced by the temperature. In fluid, okay, I should not say in fluid, because in gas again this will be different. I am not going into that part, because say in gas the viscosity is derived from a different phenomenon, but in fluid it is a different phenomenon. So, I mean that in case of liquid, fluid means in case of liquid, in case of liquid, with the increase of temperature the viscosity decreases. So, that way in case of gas this molecular movement is important, but here it is not like that. So, that is why in case of liquid, with the temperature increase the viscosity changes, and that is why it affect the frictional resistance. Okay. So, these are the laws that we can say that which affect the friction in a pipe in laminar flow. Now, let us see how these laws changes in case of turbulent flow. Well, in case of turbulent flow, the friction is proportional to the velocity to the power n. It is not directly proportional to the velocity. It is not linearly varying with velocity. It is varying exponentially. So, the friction is proportional to the velocity to the power n, and this n value varies from 1.72 to 2, from 1.72 up to 2 generally. It is found experimentally, and for most of our actual calculation we take it as 2, because if we consider 2, the calculated friction will be more, and then when we are designing considering that friction will be more, then we are in a safer side, our design will be safe. So, suppose we are trying to carry the water up to a certain extent, and if we consider the friction to be less, then we are in problem, we will be assessing less. But if we consider friction to be more, then we will be considering the loss will be more, and then we will be putting more height, and we are in the safer side. As we do not know very exactly what the n value will be for different cases, So, generally for most of our practical purpose we consider this to be 2. So, we can say that friction is proportional to square of the velocity. Well, then again it is independent of the pressure, that is same as laminar. Then it is proportional to density of the flowing fluid. Well, so density of the flowing fluid is significant here. So, it is proportional to density of the flowing fluid. And as such, like laminar flow, here also the friction is proportional to the contact surface area. It is same whether it is turbulent or whether it is laminar, contact surface area is always important. That means longer the pipe, longer will be the loss. So, that we should be careful. And then, but here what the difference is with laminar, that here the friction in turbulent flow, the friction depends on nature of the surface. Friction depends on nature of the surface. Why? Say in laminar flow, well, let me draw a diagram here. Say in laminar flow, we can say if it is the pipe, then velocity will be, we are not drawing velocity here, sorry, my circles become eccentric here, I should take here like this. Well, if I consider different layer of flow, different layer of water flowing through the pipe, because in laminar each of this layer we can say that they are flowing in layer, this is, they are not getting mixing up. If this is the layer flowing, it will be moving like that, this is moving like that, so these are not getting mixing up. Well, that is why the layer which is just in contact with the surface is forming, or it is covering the frictional roughness, say roughness of the pipe it is covering, and the other things are moving, it is in rest. So, that is why the nature of surface was not that much important. But in turbulent flow, if it is a turbulent flow, then the flow are not moving like that in layer, say it is just moving as a single flow. Once this particle is here, this next moment can go here, once the particle is here, this next moment can come here. So, that way all mix up flow is moving through this pipe. In that case, the fluid particles are always moving in a mixing way, and so these are not getting, so the particle which is in touch with the surface just at a moment will be moving into the fluid, and that way they are getting mixing up. So, there is no question of having a layer formed at the surface, and as such the frictional characteristic or the roughness characteristic of the pipe surface, inside surface of the pipe is significant, and that is why it depends on the nature of the surface. That is why, say, when we will be getting the equation of friction for turbulent flow, we will be finding that yes, this roughness parameter is coming. But when we get a equation for friction in case of laminar flow, then we will be finding that there is no such parameter. The friction parameter, the roughness parameter is not coming. Well, then this get affected slightly by variation of temperature. Well, in case of turbulent flow, otherwise also flow is very moving with mixing up, and that is why this viscosity part is already, say, get affected by this sort of movement, and in that sort of flow the effect of temperature is not that much significant. It gets affected, but slightly. The reason is that the viscosity become more significant when the fluid is moving in layer, when the fluid is moving in layer. When the fluid is in turbulent flow, so this is not that much significant, and that is why we can find that it gets affected, but it gets affected slightly by the variation in temperature. Well, so these are some of the laws or some of the facts that is being observed by the investigator through experimentation, that how the friction get influenced in laminar flow and in turbulent flow. Well, here we are just mentioning, and we are always drawing the pipe. Whenever we talk about pipe, we draw a circle or we draw a cylindrical pipe. But we should keep in mind that pipe not necessarily mean that it should be a circular. Of course, for our advantage, because of many other advantages, we go for circular section, but sometimes the pipe can be square also. There is no restriction, in fact, that pipe should be circular. We can have a square pipe also. In fact, in some of the experimental setup, we find that putting square pipe is advantageous for some of the experimentation. So that way, square pipe can also be there, but for practical purpose, as we know that for handling and as some of the things are better here, so in circular pipe we go for circular section. But I mean, on principle, if the flow is moving full, then this become a pipe flow. If there is a free surface, then only it is a open channel flow. Say when we talk about rectangular section, suppose below a culvert water is flowing. Below a culvert means in that portion it is a rectangular section. So till the point when we have a free surface flowing through it, this behave like a open channel flow. And then if we analyze the flow there, we will have to apply the principle what we have studied already, friction loss or whatever it is that we need to study or that we need to apply, considering the theories and all that we have already got for open channel flow. But say during flood time, if the water level increases and suppose the culvert is there and the box was there, but it is becoming full, and in that case once it become full, we should not allow, or we should not rather consider that to be as a open channel flow, and we should not use those equations that we have already learned in open channel flow. So during flood time, we should remember that if we are trying to calculate the discharge through that section, which may be a circular, which may be a rectangular one, but it is flowing full, then we need to apply the principle of pipe flow. Well, that is one important point for our practical design. And with this, we can now move on to some of the issues that are required, some of the facts that we need to know for calculating the head loss in laminar flow. Well, one point that we need to know is distribution of shear stress. Well, say this is a pipe which is, again I am drawing it a say circular here, okay. This is a pipe and it is carrying say water through it. Well, and then at different level, if it is, well, first we are discussing laminar flow. As the flow is moving as layer, so at different level, say this is one layer, this is another layer, like that, at different layers, the shear resistance will be different, and that we call as a shear stress. So we need to know what is the shear stress or how we can have the shear stress expression. The maximum shear stress will be, of course, at the side, So this is here the maximum shear stress can be. So if we say that this is the maximum shear stress at that point, then if we draw a graph, suppose let me draw a graph, suppose this is one axis I am drawing, and at that axis if we draw shear stress, if we plot the shear stress value, this will be say maximum shear stress that we will be getting here. So I can write this is the tau max, and then shear stress as we come towards the radius, towards the center line, this is the center line, this will reduce, and then we do not know how much will be the shear stress at this point. Again it will be increasing here. So at the boundary the shear stress is maximum, and then at center, of course, it appears that if it is to be maximum here, it is to be maximum here, then we are interested to know what will be the shear stress here, or we need to know the expression for shear stress. To analyze that, let us consider this, suppose its radius is say r0. r0 is the radius of the pipe. Well, and well, here I want to draw another point, that how the velocity will be changing. Well, we will be discussing that later, but just here I want to draw that if I plot a velocity diagram, then it will be like that. Well, I am now removing this one of course, just you remember that this is a circular section we are drawing. So now velocity, if I plot here, the velocity is 0, at the side the velocity will be 0. Shear stress is maximum here, the velocity, but it is 0. At 0 means not only at this point, if I draw anywhere the velocity is 0, and velocity will be maximum at the center. That is obvious that in a pipe, if we see that velocity will be maximum at the center, and then it will be gradually changing like that, it will be gradually changing like that. Okay. And our velocity diagram maximum point is suppose up to this point, and that distance is representing the maximum velocity, say V max, maximum velocity. Okay. Well, now to analyze how this shear stress is changing, how this velocity is changing, to have all those, what we can do. So let us take a fluid element. Say length of this fluid element is delta x. Let us consider a small fluid element, and say radius or the distance up to this fluid element be r. This is r0 and that distance is r. Well, and of course we can consider that this is at a distance of y. That may not be required here, but anyway. Well, now let me draw this fluid element in a bigger dimension here. Well, I am showing that this is circular here. I am showing that this is circular here. The same fluid element, this small fluid element, I am drawing it in a little larger dimension. Now let us see that what is the force that will be acting from this side. In this fluid element, everything will always be in a balanced position. We are considering that this is moving in a balanced position or balanced condition. So we can try to see that what will be the relations between different parameters in case of dynamic equilibrium. Well, we are talking about a steady state. We are talking about a steady state, that is acceleration is equal to 0. There is no acceleration, it is moving as a steady state. And in that steady state condition where acceleration is equal to 0, then we can say that it is in dynamic equilibrium, and that is why it is moving with uniform flow velocity. And in that condition, what will be the equilibrium equation? Well, now if say shear stress at this level, if we write as tau, then what is the total surface area? What is the total surface area? Shear stress means it is the resistance force per unit area, resistance offered per unit area. So if that is tau, then we will have to get the total shear stress in this direction, shear force in this direction. What will be that? So tau multiplied by the contact area. So what is the contact area? This diameter, this radius is r, so it will be say twice pi r is the total perimeter length. Perimeter length is twice pi r. And then we are already writing that this length is delta x. This length is delta x. So twice pi r into delta x will give us the total area of this small cylindrical element. So what will be the total force? Shear force rather, which is acting in the opposite direction, which is opposing the flow, that will be the shear stress tau into twice pi r into delta x. Well, so that we are having as resistance force. Then what are the other forces acting on this fluid element? One is that if we consider the pressure at this point as P, then this pressure, suppose pressure at this point is P, then P multiplied by the area, sectional area. So that will give us the pressure force from this direction. So area is equal to pi r square, and the pressure at this point is P, so P pi r square. Now of course there will be a pressure force in the other direction also. Now if the pressure force from the other side, we can write in terms of, say, gradient, pressure gradient. If we say that pressure from here to here is changing, that means from upstream to downstream is changing, and the pressure gradient if we write as dp dx, then what will be the pressure at this point? Say P plus pressure gradient means we are talking about with x, with downstream direction with x, how the pressure is changing. So, if it is dp dx is the pressure gradient, then at a distance of delta x, the total change in pressure will be dp dx into del x. Del x is the length of this portion. So, that will be the pressure from this side. Of course, we are not considering whether pressure is dropping in that direction or not right at this moment, but when we will do the equation, it will automatically come. We are saying that dp dx is the pressure gradient. It may happen that dp dx is negative, means pressure is dropping in the downward direction. Well, that we are not specifically mentioning at that point. And then the area is pi r square. Well, so now we can draw the equilibrium equation. So, equilibrium equation now we can write, say well, velocity distribution we will be talking later. So, equilibrium equation just we need to equate these forces from this direction and that direction. So, we can write P pi r square minus P plus dp dx into delta x into pi r square minus, this is also opposing the opposite in the opposite direction, this shear stress. So, shear force. So, tau into twice pi r into delta x. Well, that is equal to 0. That means all the force, if we add up considering its direction, finally we should get 0 when it is in dynamic equilibrium. Well, then this will lead us, if we simplify these things, say P pi r square and then this P pi r square, that will get cancelled, dp dx will remain here, dp dx and pi r square will be remaining here, that will be equal to tau twice pi r dx, dx cancel. Then we can finally get, say, pi getting cancelled, r1 r will be remaining, and then 2 will be remaining. So, it will become r by 2, and what we can have, the tau is equal to minus dp dx into r by 2. We just need to simplify this part, and then we will be getting this expression. And of course, this relation, although we are drawing for, say, laminar flow, this also accepted to be holds good for turbulent flow also. Well, now this expression, from this expression what we are finding, that is the shear stress vary linearly in laminar flow. Of course, shear stress varies linearly with r, and of course, this is accepted for turbulent flow also, I am saying. So, that way it will be valid there also. Shear stress varies linearly with r. That means, say, with radius, with the increase of radius, shear stress will increase, it will vary linearly. That means, from here to this point we will be having a straight line. And then at r is equal to 0, so one point what we are observing, that shear stress varies linearly, with r, linearly with radius or r, say radial distance we can call it, radial distance. And then another point what we are getting, that at r equal to 0, tau is equal to 0, shear stress equal to 0. So, shear stress here will be 0, and that's why now we can draw the shear stress diagram like this, because we know that it varies linearly. So, it will be straight line, and here it is tau max and here it is 0. So, this is what the shear stress diagram. At any point, if we want to find out what is the shear stress, we can calculate like this, just from this equation. Well, now let us see how the velocity distribution in laminar flow varies. Well, so let us just talk about the velocity distribution. We will be referring to this diagram again, but for velocity distribution in laminar flow, we can start with one relation, that is, we know that shear stress from our very fundamental law of viscosity, that when we were talking about coefficient of viscosity in fluid mechanics, that has already been discussed. I mean, not in this class, but you are supposed to know those things which are coming in fluid mechanics. Okay. So, that way, so tau, we can write that shear stress tau is equal to mu into dV dr. So, change of velocity with respect to r. This is in open channel flow, we can write dV dy, which it is changing, but here it is dV dr. That means with distance it is changing from that point, and this here we can write as with negative sign. So, then we can move to why we are writing negative sign, because dV dr, that is the velocity. If we move, if I draw the pipe here, then this is the center line. If I am moving, if my r is increasing, velocity, flow velocity is decreasing, as we did draw the velocity diagram tentatively like this. Velocity diagram will be like this, and then in this velocity diagram it is clear that with the increase of r we are taking from this point with the increase center line. So, with the increase of r the velocity is dropping. So, that is why we are writing tau is equal to minus sign is coming from that part, the dV dr. Okay. Now, this implies that dV dr is equal to, because already we have got one expression that if we just go back, the tau is equal to dP dx into r by 2. So, if we just put that here, that means if we put that expression tau is equal to dP dx by these things, what we will be getting, that this is equal to r by twice mu into dP dx. Just we need to put the value of tau as that one, then we will be getting dV dr is equal to like that. Well, this dP, this P is also equal to WH, as we know. So, for if we write in terms of H, this dP dH can be written as dP dx, can also be written as say W into dH dx. Of course, if Z is coming, that will be again a different issue. Here we are not talking about that part. So, this can be replaced by that part also, but here we are happy with this one. Let us proceed from this point. So, what we can do now, that is integrating. Now, we can integrate this part, that dr we will be taking to that side. So, this implies dV is equal to r by twice mu dP dx into say dr. So, integrating, what we will get. Well, so integrating this expression, what we will be getting, that V is equal to just integration of this one. So, it is r square by 4 mu and dP dx. Okay. So, then a constant of integration will be coming C, but we need to know what this value of C will be. For that, we need to take help of boundary condition. Well, now what is our boundary condition here? Say, when we are talking about velocity V, at the boundary this will become 0. At boundary, what is our r value? This will become r0. From here, if we go, this become r0. So, at r equal to r0, our V is equal to 0. So, with that boundary condition, we know that r equal to r0, V is equal to 0. So, this will imply that C is equal to, we can write say r0 square by 4 mu into dP dx. Well, then what will be our expression, final expression? So, we can write that putting this value, putting this value of C. Therefore, we can write that V is equal to this minus that. Of course, we can write this at the beginning. So, we can write minus 1 by 4 mu into dp dx into r0 square minus r square. Where we are writing like this because we know that r0 is the radius which will be always larger than distance to any section within the pipe. So, we are putting r0 square minus r square here, and then we are putting a negative sign here. Well, so that way we can get the velocity expression for velocity. Now, what will be the maximum velocity? We can write, okay, velocity we have got. Now, let us see what will be the maximum velocity that we can write. That maximum velocity say V max, and maximum velocity will be getting, as we can see this expression, when our r will become 0, that will become say maximum velocity. So, we can write the maximum velocity expression as 1 by 4 mu and minus dp dx, the negative sign we are bringing here, into r0 square. So, that is what the expression. And as we remember that earlier we were putting dp dx straight without considering or writing that as a positive, but in reality dp dx will become negative because the pressure will always be dropping in the downward direction. But we did not consider when we started the derivation, as we are not considering that condition, that dp dx, we are writing positive, but in reality the velocity will be, the pressure will be dropping in the downward direction. So, it is finally coming as negative, and that negative sign will make the entire things positive. So, that will give us the V maximum. Okay, the value will be dp dx coming as negative. So, this minus sign, ultimately V max will be getting as maximum at this point. Well, then of course, you can have a relation between, say what is the relation between, or say we can say velocity at any point in terms of, say velocity at any point, or rather at any distance in terms of say V max, that we can write now straight away, that is V, that means V at any time is equal, if we know V max, which in real condition also we can measure, say V max at the center, if we measure, then we will be getting the V max into 1 minus r square by r0 square. Well, so just V max by V, if we do, both the equation are remaining in different field. You can observe this equation, and you can see this equation. If we divide this by that and taking r0 common, if we bring r0 common here, this will be 1 minus r square by r0 square. So, that r square and this other part will be getting cancelled, and this will remaining. So, that way we can get what the expression for V is. Well, now we can talk about average velocity. What is the expression for average velocity? Okay, what is average velocity? Say when we talk about this pipe, if we see that this is the velocity distribution diagram, it is almost triangular, and then we know that this area is equal to pi r0 square rather. This area is equal to pi r0 square. Well, so if it is pi r0 square, then the total discharge will be equal to, say discharge is equal to, say just to explain that, it will be, suppose if I consider a small area, and at that small area the velocity is this much. So, in unit time, how much discharge is flowing? This area multiplied by this velocity. So, that is the total discharge flowing. Okay. So, that means area into this velocity will give us the discharge. So, that way if I consider another small area, this area into this velocity will give us the discharge. That way if I consider all the smaller area, then we will find that this will give us the discharge. That means, what indirectly means that if I consider all the area, the entire covering area, that is the triangular area, what we are getting, nearly triangular area, that will give us the discharge. So discharge Q, we can write that this is pi r square. So what we can write, discharge Q is equal to, say, this triangular area means half of base into altitude. This base is equal to pi r square. I mean pi, it is conical basically, pi r square, and it is into height. So half of pi r0 square into the height means we are talking about V max. Height means we are talking about this V max. This is the height. Okay. Well, so let me put, say, this is the V max here. Well, so this discharge Q is equal to half of pi r square into V max. Now we are interested in average velocity. If we talk about average velocity, then average velocity, again we can have in terms of average velocity, what we can have in terms of average velocity, we can write the discharge as, say, Q is equal to average velocity V average into the area. Area is equal to pi r0 square, and these two must be same. So from that, this is, say, if it is 1, this is 2. So 1 and 2 implies that V average is equal to this divided by, say, half of pi r0 square V max divided by pi r0 square. So this is equal to half of V max. So that is, of course, we have done some approximation here, but still we can get very conveniently that average velocity is equal to half of the V max. Well, so that is how we can get an expression for average velocity. Now considering this equation, or now using the expression for V max here, V max already we have one expression, so we can write V average is equal to, say, half of V max, that we can write as, say, 1 by 8 mu, that means from this expression 1 by 8 mu, and other part will remain same, 1 by 8 mu minus dp dx into r0 square. So this is the expression for velocity in pipe, because when we are writing V as a velocity at any section, we must write about the average velocity. So though here we are writing average velocity, from this point onward, when we will be talking about velocity at a particular section V, means we are meaning the average velocity, because for calculation of discharge also we are using the same velocity, and that way it will be convenient for us to have all other discussion in that line. And from this point, what we can do, that V average is equal to this part, well, then this lead us to one expression which is called Hazen-Poiseuille equation, which is of quite important in, quite importance in our study of pipe flow. Well, so this Hazen-Poiseuille equation, how we can derive, already we have got that V average, now we are writing as V. V is equal to, say, 1 by 8 mu, then minus dp dx into r0 square. Okay. So pressure difference, now we can just have it in different form, and what we can write, that 8 mu V, just changing it to this side, 8 mu V, and then on the right hand side divided by r0 square, of course, r0 square, then we are keeping the dx here, is equal to minus dp, is equal to minus dp. Now if we integrate this one, integrating, what we will be getting, integrating, say dp, if we integrate, we will be getting p1 minus p2, p1 minus p2, and that is equal to, say, 8 mu v r0 square into dx, we can replace by x2 minus x1. And what is x2 minus x1? This part is nothing but the length of the pipe, length of the pipe. So what we can write finally, and that p1 minus p2 P1 minus P2. In fact, once we integrate, it will be coming as P2 minus P1, but it is a negative, so we are getting at P1 minus P2, and P1 minus P2 is equal to, say, now we can write in terms of L. So, and suppose if we want to replace this R0, that is, generally in case of pipe we will be getting diameter. So, if we want to replace this as diameter, then this is basically d by 2 square. So, we will be what we will be getting d square by 4. So, replacing this by d, so it will become d square by 4, and that 4 we are writing here. So, 4 into 8, this will become 32 mu v into L. So, that is one important equation and is called Hazen-Poiseuille equation. Well, and starting from that equation, now we can have what is head loss. Our interest to know head loss. Head loss is equal to basically P1 minus P2 by L, because Z we are considering, we are not considering here. So, P1 minus P2 by, sorry, W. If we divide it by W, P1 minus P2 by W, that will give us the head loss is equal to, we can write 32 mu V L divided by W d square. Okay. Well, so we have got one expression for head loss. Ultimately, after doing all this calculation and all this rather derivation, and that head loss is for laminar flow. We will be discussing further more on that, and we will see if it is turbulent flow, how we can have the equation for head loss, and can we have a general expression which can be used for calculating head loss in pipe. That will be seen in the next class. Thank you very much.